The universe is a story where we have only read the first page. We have mapped planets, understood starlight, and even heard the echo of the Big Bang itself. Yet for every answer, a deeper, more profound question emerges from the cosmic dark. Today, the greatest puzzles in science are not about what we see, but about the overwhelming, invisible reality we cannot. By the end of this journey, you will confront 30 questions that define the very edge of human knowledge, from the ghostly pull of dark matter to the true nature of time itself. We will ask what happened before the Big Bang and why the cosmos seems eerily silent of other life. What single cosmic mystery keeps you looking up at the night sky? Our story begins not with what we see, but with what we feel. The first question on our list is perhaps the most humbling. What is dark matter? We know it is there. We can see its shadow moving across the cosmos. When astronomers measure how fast stars orbit the center of their galaxies, they find something deeply unsettling. The stars on the outer edges are moving far too quickly. Based on the amount of glowing matter we can see, the stars, the gas, the dust, the immense gravity of the galaxy's core should not be strong enough to hold onto these distant stars. They should be flung out into the void like children spun off a merry-go-round, but they are not. They are held in place by an invisible hand. Something with immense gravity, something we cannot see, is holding the entire galaxy together. This same ghostly grip is seen in clusters of galaxies, where the visible mass is nowhere near enough to keep the cluster bound. The only explanation is a vast, unseen scaffold of matter, a cosmic skeleton upon which the luminous universe is draped. We have named this phantom dark matter, and it is not a small component. It makes up roughly 27% of everything in the universe. All the stars, planets, and nebulae you have ever seen in photographs account for less than 5%. We are the rare exception. The universe is dominated by shadows, so what could it be? The leading ideas are as strange as the phenomenon itself. One candidate is called a WIMP, which stands for Weakly Interacting Massive Particle. These are hypothetical particles, heavy and slow-moving, that barely interact with normal matter except through gravity. They would stream through you, through the Earth, as if nothing were there. To catch one, scientists have built exquisitely sensitive detectors and placed them deep underground, in old mines or beneath mountains, to shield them from the constant rain of cosmic rays. They wait in the quiet dark, hoping for a single, telltale tremor as a WIMP bumps into an atomic nucleus. Another candidate is even more peculiar, a particle called the action. Theorized to be incredibly light, billions of times lighter than an electron, actions would behave more like a pervasive, sloshing fluid than discrete particles. Experiments are searching for them by trying to convert them into faint photons in powerful magnetic fields. The truth is, after decades of searching, we have not caught anything definitive. We are like people in a sealed room, feeling a persistent, powerful draft, but unable to find the crack in the wall. Solving this mystery is not just an academic exercise. Dark matter's gravity was the seed from which all galaxies grew. Without it, stars would never have clumped together, and the universe would be a formless, dark soup. To understand our own origins, we must first understand the nature of the dark. Yet for all its mystery, dark matter is a force of cosmic construction, holding the universe together. The second question reveals a force doing the exact opposite, tearing it apart. What is dark energy? If dark matter is the unseen glue, dark energy is the phantom pressure, an anti-gravity that is causing the expansion of the universe to not just continue, but to accelerate. This discovery in the late 1990s was so shocking it earned a Nobel Prize. Astronomers were measuring distant supernova, the titanic explosions of dying stars, to gauge how fast the universe was expanding. They expected to see the expansion slowing down over time, as the collective gravity of all matter in the cosmos pulled back on the initial momentum of the Big Bang. It was like throwing a ball into the air, expecting gravity to eventually bring it back down. Instead, they saw the ball speeding up, racing away faster and faster. The most distant supernovae were fainter than they should have been, meaning they were farther away than expected. The universe's expansion was accelerating. Something was overpowering gravity on the grandest scale imaginable. The leading candidate for this something is Einstein's cosmological constant, a term he originally inserted into his equations of general relativity to force a static, unchanging universe. When Edwin Hubble later proved the universe was indeed expanding, Einstein called this addition his biggest blunder and removed it. Now, it seems he may have been right for the wrong reason. The cosmological constant represents a constant energy density inherent to empty space itself. Think of the vacuum of space not as truly empty, but as a seething quantum foam where virtual particles flicker in and out of existence. This quantum jitter should impart a tiny energy to every cubic centimeter of nothingness. When you add up all that nothing across the vastness of the cosmos, you get a repulsive force of staggering power. The problem is the numbers do not match by a lot. Quantum field theory predicts a vacuum energy value that is 120 orders of magnitude too large. That is a 1 followed by 120 zeros. If that prediction were correct, the repulsive force would have ripped atoms apart before they could even form. So our best theories are catastrophically wrong about the energy of empty space. This is the vacuum energy problem, one of the worst mismatches in all of physics. Whatever dark energy truly is, it is the dominant component of our universe, making up about 68% of everything. Its nature will write the final chapter of cosmic history. If it continues to accelerate expansion, it leads to a cold, lonely fate called the Big Freeze, where galaxies are ripped apart, stars fade, and the cosmos becomes an ever-thinning, dark and silent void. Dark matter and dark energy shape the cosmos, but they cannot answer the question of its birth. We now face the third and perhaps most profound mystery on our list. What happened before the Big Bang? Our entire understanding of physics, the very concept of cause and effect, breaks down at this point. We can trace the universe's history back to an unimaginably dense, hot, and tiny state, but our equations hit a wall at a moment called the Planck time. This is the first tiny fraction of a second after the Big Bang, a scale so minute that the classical laws of gravity and quantum mechanics collide into nonsense. At this singularity, all matter and energy were compressed into a point of infinite density, and our models simply stop working. It is like asking what is north of the North Pole. The question itself may be flawed because time, as we understand it, may have begun with that event. Asking what came before the beginning of time might be meaningless. Yet the human mind rebels against this idea. We are wired for narrative, for a before and an after, so scientists have proposed breathtaking theories to provide a context for that first moment. One leading idea is cosmic inflation. This theory suggests that a fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion, smoothing it out and seeding the structures we see today. But some versions of inflation are eternal, suggesting our Big Bang was not a unique beginning, but just one bubble in a frothing, endless multiverse of universes, each with its own laws of physics. In this view, our cosmos is one leaf on an infinite tree, and the question of a true beginning recedes forever. Another compelling model is the cyclic universe. Imagine two parallel sheets of reality, called brains, floating in a higher dimensional space. These brains could periodically collide, each collision releasing immense energy that we experience as a Big Bang, followed by expansion, then a slow drawing together for the next collision in an endless cycle. Our universe would have no true beginning or end, just an eternal rhythm of creation and destruction. Then there is the quantum gravity approach, which suggests that the singularity is an illusion. In this view, a previous universe could have contracted to a very dense state, then bounced into our expanding one like a cosmic rubber ball. Time would have existed before our Big Bang, but in a form we cannot yet describe. To grasp this, think of time not as a universal river flowing in one direction, but as a dimension that can curve, twist, or even emerge from a more fundamental reality. The challenge is not just scientific, it is deeply philosophical. We are trying to use a tool, our physics, to examine the factory where the tool itself was made. The answer, if there is one, will forever change our story of existence. It moves us from asking what the universe is to asking why it is anything at all. The silence of the cosmos is perhaps its loudest mystery. We have just pondered the violent birth of everything, a universe forged in fire and expanding into a canvas of countless stars. With hundreds of billions of galaxies, each home to hundreds of billions of suns, the numbers scream that we cannot possibly be alone. And yet, when we listen, we hear nothing but a profound and unsettling quiet. This is the fourth great question. Are we alone in the universe? The contradiction between the high probability of life and the complete lack of evidence for it has a name, the Fermi paradox, named for the physicist Enrico Fermi, who, over a casual lunch in 1950, famously asked, "But where is everybody?" The math seems undeniable. In the 1960s, astronomer Frank Drake created a framework to estimate the number of communicative civilizations in our galaxy. The Drake equation is not a formula with one answer, but a series of variables that force us to confront our ignorance. It starts with the rate of star formation in the Milky Way. Then it asks what fraction of those stars have planets. How many of those planets are in the habitable zone where liquid water could exist? On how many of those does life actually arise? And of those life-bearing worlds, how often does that life evolve intelligence? How often does that intelligence develop technology capable of broadcasting signals into space? And finally, what is the average lifespan of such a technological civilization? Plug in optimistic numbers and the galaxy should be buzzing with conversation. Plug in pessimistic ones and we might be utterly unique. Our recent discovery of thousands of exoplanets has filled in some early variables with stunning success. We now know planets are common and rocky worlds in habitable zones are not rare. This makes the subsequent silence even more puzzling. If the universe is so fertile, why does it feel so empty? This is where the great filter hypothesis enters, a chilling and compelling answer to the paradox. The idea is that there is at least one enormous, perhaps insurmountable, barrier that prevents life from progressing to the stage of interstellar civilization. The terrifying question is, where is this filter located? Is it behind us? If the filter is in our past, it means the step from non-life to simple life, or from simple life to complex, intelligent life, is astronomically rare. We got incredibly lucky, and most planets with the right conditions never make it this far. This is an optimistic view for humanity, suggesting the hardest part is over. The alternative is far darker. What if the great filter is ahead of us? This suggests that the step from a technological civilization like ours to a star-faring one is almost always fatal. Perhaps every advanced culture eventually creates its own doom, through nuclear war, environmental collapse, artificial intelligence, or some technology we have not yet dreamed of. In this scenario, the eerie silence is a cemetery filled with civilizations that flashed brightly and then vanished. Other solutions are less apocalyptic but equally mind-bending. The zoo hypothesis suggests we are in a galactic wildlife preserve, that advanced civilizations are aware of us but have chosen a strict policy of non-interference, observing us from a distance until we reach a certain maturity. Or perhaps the vast distances between stars are simply too great, making physical travel impractical and communication a game of patience spanning millennia. A signal from a civilization 1,000 light-years away would take 1,000 years to reach us and another 1,000 for our reply. conversations become monologues stretched across eons. Maybe other intelligences are out there, but they communicate in ways we cannot begin to perceive, using neutrino streams or gravitational waves, technologies that are still magic to us. Or perhaps the most haunting answer is the simplest. We are, in fact, the first. In the grand timeline of the universe, complex life may have needed specific cosmic conditions that only recently aligned. We might be the pioneers, the early bloomers in a galaxy that will one day teem with life, but for now we are utterly, profoundly alone with our questions. The search continues, with radio telescopes scanning the skies and probes carrying messages into the void. Every silent frequency is an answer in itself, whispering a story we are still learning how to hear. This profound silence forces us to look not just outward but forward to the ultimate destiny of everything we see. The fifth question asks, what is the ultimate fate of the universe? The answer depends on a cosmic tug-of-war between two invisible forces, the relentless pull of gravity from all matter and the mysterious push of dark energy. The outcome will be written in the very shape of space-time itself. Cosmologists describe this shape with a simple but profound concept, the critical density. Imagine space as a flat, infinite sheet. If the average density of matter and energy in the universe is exactly at this critical value, the universe is flat and will expand forever, but at a rate that slows toward a stop. If the density is higher, the universe has positive curvature, like the surface of a sphere. In that case, gravity eventually wins, pulling all matter back together in a cataclysmic reversal. If the density is lower, the universe has negative curvature, like a saddle, and expansion accelerates unchecked. Our best measurements from satellites like Planck suggest we live in a universe that is remarkably flat or very close to it. But because of dark energy, this flatness leads not to a gentle slowdown but to a runaway acceleration. This points toward a chilling end known as the Big Freeze or heat death. In this scenario, dark energy continues to stretch the fabric of space faster and faster. Over trillions of years, galaxies beyond our local group will be pulled away, their light stretched beyond visibility. Star formation will cease as interstellar gas is dispersed. Existing stars will burn out one by one, leaving behind cold stellar corpses, black holes, and frozen planets. Eventually, even black holes will evaporate over unimaginable timescales through a process called Hawking radiation. The universe will approach a state of maximum entropy, a uniform, dark, and frigid sea of diluted particles and radiation, where no energy can be harvested to do any work. It is the ultimate thermodynamic silence, but the Big Freeze is not the only possibility. If dark energy is not a constant force, but something that grows stronger over time, a far more violent end awaits: the Big Rip. In this model, the repulsive force of dark energy increases without bound. First, it would tear apart galaxy clusters, then individual galaxies. As the acceleration becomes overwhelming, it would rip stars from their galaxies and planets from their stars. In the final moments, even atoms would be torn apart as the nuclear forces holding nuclei together are overcome. The fabric of spacetime itself would be shredded. The universe would end not with a whimper but with a catastrophic, fundamental dissolution of reality. There is a third, more cyclical classic ending: the Big Crunch. This was the favored model before the discovery of dark energy. If the density of the universe were high enough, gravity would eventually halt and reverse the expansion. Galaxies would begin rushing back toward each other. The universe would heat up as it compressed, the cosmic background radiation becoming first a warm glow, then an oven, then a forge. All matter would be compressed back into an ultra-hot, ultra-dense state, perhaps another singularity, a mirror of the Big Bang. This leads to fascinating modern theories like the Big Bounce, where a collapsing universe rebounds into a new expanding one, creating an endless cycle of cosmic death and rebirth. Our current data strongly disfavors a big crunch, but physics at the extremes of density is unknown territory. Even more speculative is the idea of vacuum decay. This stems from quantum field theory, which suggests our universe might not be in the true, lowest energy state of the vacuum, but in a false, metastable one. Think of it like a ball resting in a small dip on the side of a hill. It seems stable, but given a big enough nudge, it could roll down into the valley far below. If a quantum event triggered such a transition in some corner of space, a bubble of true vacuum would form and expand at the speed of light, rewriting the laws of physics as it goes. Everything in its path, atoms, forces, life itself, would cease to exist in any form we recognize. The universe would be rebooted with a new, alien set of rules. The unsettling truth is that we do not yet know which of these fates, if any, is correct. Our measurements of dark energy's properties are still too uncertain. Is it perfectly constant, or does it evolve? The answer will decide the final chapter of the cosmos. We are like sailors who have just mapped the shoreline of a vast ocean, trying to predict where the currents will take us over a voyage that will last 100 trillion years. The destination remains hidden in the dark. The ultimate fate of the cosmos is written in the behavior of its most extreme inhabitants. A black hole is not just an object, it is a place where the universe itself is broken. We understand the outer layers well. Imagine a star many times more massive than our Sun collapsing under its own gravity. Its outer layers explode in a supernova while its core crushes down past the point of no return. This creates a boundary in space called the event horizon, a one-way membrane. Outside this horizon, physics is strange but familiar. The gravitational pull is so intense that to escape it, you would need to travel faster than light, which is impossible. Cross that invisible line and you are committed. No signal, no light, no particle can ever come back out to tell the tale, but what happens to you then? According to Einstein's theory of general relativity, you would be stretched into a long, thin strand of atoms in a process called spaghettification, pulled inexorably toward the center. And at that center lies the singularity, a point of infinite density where the curvature of spacetime becomes infinite and all known laws of physics cease to have meaning. It is a mathematical error in the heart of reality. This is where our comfortable understanding ends and the true mystery begins. The clash between general relativity, which governs gravity and the large-scale structure of the cosmos, and quantum mechanics, which rules the subatomic world, creates a paradox that has divided physicists for decades. It is called the black hole information paradox. Quantum mechanics states that information about the state of a particle, its spin, its charge, its quantum identity, can never be truly destroyed. Yet, if something falls into a black hole, it seemingly vanishes from our universe forever, taking all that information with it. When the black hole eventually evaporates over eons through Hawking radiation, that radiation appears to be random thermal noise containing no information about what fell in. This would mean the information is permanently lost, violating a fundamental quantum rule. To resolve this, some physicists proposed a shocking idea, the firewall. The theory suggests that at the event horizon, instead of a smooth passage, there is a blazing wall of high-energy particles that would incinerate anything crossing it. This would preserve information by preventing anything from actually entering the black hole in the traditional sense, but it violates Einstein's principle that someone falling in should not notice anything special at the horizon. It is a paradox within a paradox. Other theories are even more radical. The holographic principle suggests that all the information about what fell into a three-dimensional black hole is not lost inside, but is encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared on its surface. The three-dimensional interior we imagine might be a projection, an illusion. This leads to wilder speculations. Could a black hole be a tunnel, a wormhole, connecting to another point in space and time, or even to another universe entirely? The equations allow for such structures known as Einstein-Rosen bridges, but they would be unimaginably unstable, collapsing instantly unless propped open by a hypothetical form of exotic matter with negative energy. And if a wormhole is one end of a cosmic tube, what is the other? Some models suggest a white hole, a theoretical region of space-time that can only eject matter and energy, the opposite of a black hole. While no white hole has ever been observed, they represent a tantalizing mathematical possibility, a place where the universe might be birthing new matter instead of consuming it. To stand before a black hole is to stare into the ultimate unknown, a laboratory for laws of physics we have not yet written. It is a reminder that our universe may be far stranger and far more connected than we have ever dared to dream. From the violent heart of a black hole to the quiet chemistry of a warm tide pool, the universe's greatest trick was turning stardust into something alive. Our seventh question brings the mystery home. How did life begin on Earth? This is the puzzle of abiogenesis, the leap from non-living chemistry to a living, self-replicating cell. It is a transition so profound we have found no fossil of the event itself, only the tantalizing clues left in its wake. The story begins in the early 1950s with a landmark experiment by Stanley Miller and Harold Urey. They wanted to test if the basic ingredients for life could arise naturally. They took a flask of water to represent the ancient ocean and filled another with gases they believed made up the early atmosphere: methane, ammonia, and hydrogen. They then sparked this mixture with electrodes to simulate lightning. After just 1 week, the water turned a murky brown. When they analyzed it, they found amino acids, the fundamental building blocks of proteins, which are essential for all life as we know it. It was a stunning result. The experiment proved that the complex organic molecules necessary for life could form spontaneously from simple ingredients and energy. But the real universe had an even bigger head start. We now know that space itself is a vast chemical factory. Spectroscopic analysis of interstellar gas clouds and observations of comets have revealed a rich soup of organic compounds out there, including sugars and the nucleobases that form DNA. It seems the raw materials for life were raining down on the young Earth from the very beginning, delivered by asteroids and comets, so the building blocks were present. But how did they assemble themselves into something that could be called alive? This is the chasm between chemistry and biology, and bridging it is the core of the mystery. One leading theory is the RNA world hypothesis. The problem with the classic chicken and egg scenario is that DNA needs proteins to replicate, but proteins are built using instructions from DNA. RNA, a close chemical cousin of DNA, offers a way out. It can both store genetic information like DNA and catalyze chemical reactions like a protein. The idea is that before DNA or proteins existed, a world of self-replicating RNA molecules emerged in the primordial soup. These molecules would have competed for resources, evolved through natural selection at a chemical level, and eventually learned to build protective membranes and more efficient machinery, leading to the first primitive cells. The environment for this genesis is hotly debated. Some scientists point to warm little ponds, as Charles Darwin once mused, where cycles of wetting and drying could concentrate molecules and foster reactions. Others champion deep-sea hydrothermal vents, the spectacular black smokers on the ocean floor. These mineral-rich chimneys provide a constant flow of energy and a labyrinth of microscopic pores that could have acted as natural test tubes, concentrating organic molecules and protecting them from the harsh surface conditions of the early Earth. Then there is the more cosmic idea of panspermia. This suggests that life, or its direct precursors, did not originate on Earth at all, but was seeded here from elsewhere. Perhaps a comet carrying hardy bacterial spores crashed into our planet, delivering the spark. While this elegantly sidesteps the problem of Earth's origins, it simply pushes the mystery farther out into the cosmos. We still must explain how life began somewhere under some conditions. The frustrating truth is that we have a compelling outline of the story, but the central chapter is missing. We know the actors, the amino acids and nucleotides. We know several possible stages, like the warm pond or the deep sea vent. But we do not know the precise sequence of events that transformed a complex, lifeless chemical system into a simple, living one that could eat, grow, and replicate. It is the difference between having a pile of exquisite watch parts and understanding the exact moment the gears meshed and the hands began to turn. That moment when chemistry became biography remains one of the most profound and elusive turning points in the history of our universe. The leap from chemistry to life feels like a miracle, but it is grounded in the laws of our universe. What if our universe, with its specific laws that allow for such miracles, is not the only one? This leads us to the eighth monumental question. Is there a multiverse? The idea of parallel realities has long been the domain of science fiction, but in recent decades it has emerged as a serious, albeit controversial, scientific possibility. It is not a single theory, but a consequence that falls out of our most ambitious attempts to explain the cosmos. The first path to the multiverse comes from the theory of cosmic inflation. You will recall that inflation was the period of hyper-fast expansion just after the Big Bang. Some versions of this theory are eternal. In this model, once inflation starts, it never completely stops. The inflating space spawns bubble universes like foam in an endlessly boiling pot. Each of these bubbles undergoes its own Big Bang, cooling into a universe with its own random set of physical constants and laws. Our entire observable cosmos is just one bubble in an infinite, ever-growing froth of realities. This is what cosmologist Max Tegmark calls a level 2 multiverse. In these other bubbles, the fundamental forces might be stronger or weaker. Gravity might not exist, chemistry might be impossible, or it might create forms of matter we cannot conceive. The second major path comes from string theory, the leading candidate for a theory of everything that attempts to unify gravity with quantum mechanics. String theory suggests that at the tiniest scales, particles are not points but vibrating loops of energy. To make the math work, the theory requires extra spatial dimensions, curled up into shapes so small we cannot perceive them. The problem is, there are perhaps 10 to the 500 different ways these dimensions can curl. Each configuration corresponds to a different vacuum state, a different set of laws and constants for a possible universe. This is the string theory landscape, a vast, abstract terrain of possible realities. Our universe, with its specific laws that allow for stars, planets, and life, would be just one valley in this colossal landscape. This connects back to the mystery of dark energy. Why is the energy of our vacuum so inexplicably small and perfect for allowing galaxies to form? In the multiverse view, there is no why. It is a random roll of the cosmic dice. In an infinite number of bubble universes, every possible value occurs somewhere. We simply find ourselves in one of the rare bubbles where the numbers are right for our existence. This is the anthropic principle in its starkest form, but scientists classify multiverses into levels to keep the ideas clear. A level 1 multiverse is almost trivial. If our universe is infinite and uniform, as data suggests, then somewhere far beyond our cosmic horizon, there are regions of space where every possible arrangement of particles is repeated. There is another Earth out there, an identical copy of you reading this, and infinite variations where one atom is out of place. A level 2 multiverse is the inflationary or string theory bubbles, where even the fundamental constants differ. A level 3 multiverse comes from the many worlds interpretation of quantum mechanics. In this view, every time a quantum event has multiple possible outcomes, the universe splits. All outcomes happen, each in its own newly branched reality. In one world, the cat in the famous thought experiment is alive. In the branch right next to it, the cat is dead. This creates a mind-boggling tree of forking paths, where every choice, every chance event spawns new universes. the philosophical and scientific challenges here are immense. The core issue is testability. Can a theory that predicts an infinite number of universes we can never observe, communicate with, or measure be considered scientific? Proponents argue that if a theory like inflation is the best explanation for the features we see in our universe, and that theory inevitably predicts a multiverse, then we must take the prediction seriously. They search for indirect evidence, like looking for bruises on our cosmos from collisions with other bubble universes in the distant past, imprinted as odd patterns in the cosmic microwave background. Skeptics counter that this ventures into metaphysics. If everything that can happen does happen somewhere, then the theory explains everything and predicts nothing specific about our own world. It risks becoming untestable and therefore outside the realm of science. The multiverse forces us to confront the very nature of reality and the limits of our inquiry. Are we one universe or one page in an infinite library where every conceivable story is written? The answer, if we can ever find it, would be the ultimate cosmic perspective shift. Time is the river we all swim in, yet we understand its current no better than a fish understands water. The ninth great mystery asks, what is the nature of time? Is it a fundamental, flowing substance woven into the fabric of reality, or is it merely a powerful illusion that emerges from something deeper? Our two most successful theories of physics give us two completely different and utterly contradictory answers. According to Einstein's theory of relativity, time is not separate from space. They are woven together into a single four-dimensional fabric called spacetime. In this view, the past, present, and future all exist simultaneously. This is called the block universe theory. Imagine the entire history of the cosmos as a giant, four-dimensional loaf of bread. Every slice of that loaf is a moment in time, from the Big Bang to the distant future. From a perspective outside the block, every event, your birth, the formation of the sun, the end of the universe, is equally real and fixed in its place. There is no special now that moves. The flow of time is an artifact of our consciousness, a way our brains make sense of being stuck on a one-way journey through the block. This is a profound and unsettling idea. It means your future is already out there, as real as your yesterday. Yet, this elegant picture from relativity clashes violently with our other pillar of physics, quantum mechanics. In the quantum world, time is not a dimension to be traversed. It is an absolute background against which events unfold. Equations describe how quantum states evolve in time, but time itself is not part of the system. It is the stage, not an actor. This conflict is at the heart of our failure to create a theory of quantum gravity. We cannot reconcile a universe where time is flexible and relative with one where it is rigid and absolute. Even within the block universe, we experience a relentless directionality, the arrow of time. Why do we remember the past but not the future? Why does an egg splatter on the floor but never reassemble itself and jump back into our hand? This arrow is tied to a concept called entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Milk mixes into coffee, ice cubes melt, buildings crumble. These are all journeys from order to disorder. Our universe began in a state of incredibly low entropy at the Big Bang, a highly ordered starting point. Ever since, it has been sliding toward greater and greater disorder, and that slide is what we perceive as the forward march of time. But if time is just a dimension in a block, why is there an arrow at all? Why does entropy only increase in one direction along the time axis? This remains one of the deepest puzzles in cosmology. The mystery deepens when we ask if the flow can be reversed. Is time travel to the past possible within the laws of physics? Relativity does not strictly forbid it. Certain solutions to Einstein's equations allow for paths called closed time-like curves. These are loops in spacetime that could, in theory, allow you to travel back to your own past. One way to create such a curve would be with a wormhole, a shortcut through spacetime. If you could take one mouth of a stable wormhole and move it at near light speed while keeping the other stationary, time dilation effects from relativity would cause the moving mouth to age slower. If you then stepped into the stationary mouth, you could exit the moving mouth at a point in time before you entered. You have gone back in time, but the problems are immediate and paradoxical. The most famous is the grandfather paradox. What if you went back and prevented your own grandfather from meeting your grandmother? You would never be born, so you could never go back in time to stop the meeting. The paradox creates a logical inconsistency that seems to violate causality, the principle that cause must come before effect. Physics has proposed ways out. The self-consistency principle, or the Novikov self-consistency conjecture, suggests that the laws of physics simply will not allow you to create a paradox. Any action you take in the past was always part of history. You were always there. Your attempt to change events will inevitably fail through a bizarre conspiracy of coincidences that forces the timeline to remain consistent. Another, more radical idea is the many worlds interpretation. In this view, if you travel to the past and change something, you do not alter your own timeline. Instead, you branch off a new, parallel universe. In that new reality, your grandfather died young, and you never exist there, but you can return to your original universe unchanged. This turns time travel into universe hopping. The practical barriers, however, are staggering. To warp spacetime enough to create a time loop requires energies and densities we associate with singularities, or hypothetical exotic matter with negative energy, which we have never observed. For now, time travel remains a theoretical ghost in the equations, yet the very fact that our best theories allow us to ask the question tells us that time is far stranger than our daily experience suggests. We are not just moving through time, we are, in some fundamental way, a part of its unresolved mystery. Our existence is a cosmic statistical error, a 1 in a billion fluke that should never have happened. This is the 10th great mystery. What caused the matter-antimatter asymmetry? According to our best theories, the Big Bang should have been perfectly symmetrical. For every particle of matter created, an identical particle of antimatter should have been its mirror twin. Antimatter is not science fiction, it is very real. For every proton, there is an antiproton with a negative charge. For every electron, a positron with a positive charge. When matter and antimatter meet, they annihilate in a flash of pure energy, leaving nothing behind. If the early universe had been perfectly balanced, every particle would have found its antimatter twin. The entire cosmos would have been converted into a sea of radiation, a lifeless fog of light with no stars, no planets, and certainly no one to wonder about it. Yet here we are, in a universe made almost entirely of matter. Every atom in your body, every star in the sky, is a survivor of that near-total annihilation. Something tipped the scales. Just a tiny 1 part in a billion imbalance was enough. After the cataclysm, for every billion annihilations, 1 single particle of matter was left over. That leftover is everything we see. The question is, what broke the symmetry? Physicists call this necessary breaking CP violation. The C stands for charge conjugation, which swaps a particle for its antiparticle. The P stands for parity, which mirrors its spatial coordinates like looking at it in a mirror. For a long time, physicists believed the laws of physics were perfectly symmetric under a CP transformation. The universe, they thought, would behave the same way if you swapped every particle with its antiparticle and viewed it in a mirror. But in 1964, an experiment at Brookhaven National Laboratory shattered that belief. Scientists studying the decay of neutral kaons, a type of subatomic particle, found that the antimatter version decayed at a slightly different rate than the matter version. The mirror was flawed. This was the first evidence of CP violation, a crack in the perfect symmetry of creation. It proved that the laws of physics have a tiny, built-in preference for matter over antimatter. The discovery was so monumental it earned a Nobel Prize, but there is a problem. The amount of CP violation we have measured in particle decays is far, far too small to account for the overwhelming dominance of matter in our universe. It is like finding a single bent coin in a vast vault and trying to explain a global financial crisis. The standard model of particle physics, our current rulebook for the subatomic world, includes some CP violation, but it is insufficient by many orders of magnitude. This means our rulebook is incomplete. We are missing a source of cosmic bias. The search for this missing violation is one of the most urgent quests in physics. Scientists are hunting for it in two main ways. The first is by smashing particles together at immense energies in machines like the Large Hadron Collider. They are looking for new particles or forces beyond the standard model that could have tipped the balance in the early universe. One promising candidate is a hypothetical particle called the leptoquark, which could interact differently with matter and antimatter. Another is the search for a property of neutrinos, the ghostly particles that stream through everything. If neutrinos are their own antiparticles, a possibility known as Majorana neutrinos, they could have triggered processes that favored matter in the universe's first moments. The second approach is one of exquisite precision. Teams around the world are studying the properties of known particles and antiparticles with incredible care, looking for any minuscule difference that the standard model cannot predict. They trap single antiprotons in magnetic bottles for months, measuring their behavior to 1 part in a trillion. They compare the magnetic properties of protons and antiprotons. Any discrepancy, no matter how small, would be a monumental clue pointing to new physics. Solving this puzzle is not just about satisfying curiosity. It is about explaining the most fundamental fact of our reality, why there is something rather than nothing. We are the evidence of a broken symmetry, the living proof that the universe is not perfectly balanced. We are the rare, precious residue of a near-total annihilation, asking how we survived at all. Jupiter is a world of secrets wrapped in swirling storms. We have mapped its cloud tops for centuries, but what lies beneath those bands of ammonia and hydrogen is a puzzle that challenges our very understanding of planets. This is the 11th question. What is at the core of gas giants like Jupiter? Our standard model of planetary formation tells a straightforward story. A rocky core forms first, growing massive enough to gravitationally capture the vast primordial cloud of hydrogen and helium gas from the young solar system. That core should still be there, buried under thousands of miles of crushing pressure, but the reality may be far stranger. Jupiter's interior is a place where physics becomes extreme. As you descend, the weight of the atmosphere above increases until the pressure is millions of times greater than on Earth's surface. Under these conditions, hydrogen, the simplest and lightest element, undergoes a radical transformation. It is squeezed into a state that is neither a gas nor a solid, but a liquid metal. The electrons are stripped from their atoms, creating a seething, electrically conductive ocean. This metallic hydrogen is believed to be the source of Jupiter's immense magnetic field, the strongest in the solar system. But what of the core itself? There are two competing visions, each bizarre in its own way. The first is that a compact, rocky core does exist, perhaps 10 to 20 times the mass of Earth, forged from the heavy elements that sank to the center during the planet's formation. It would be a world of diamond and strange, high-pressure minerals, hotter than the surface of the sun. The second possibility is more unsettling. The intense heat and pressure over billions of years may have eroded and dissolved that original core. Heavy elements like iron and silicon could be mixed throughout the metallic hydrogen layer, creating a gradual, diffuse transition rather than a distinct solid ball. Jupiter might have a fuzzy, smeared-out heart. To solve this, we cannot drill, we must listen. That is the goal of missions like NASA's Juno spacecraft. By orbiting extremely close to the planet's cloud tops, Juno measures tiny wobbles in Jupiter's gravity field with exquisite precision. As the spacecraft speeds up or slows down ever so slightly in its orbit, it maps the distribution of mass deep inside the planet. Think of it like a cosmic X-ray, but using gravity instead of light. The data has already delivered surprises. Jupiter's core appears to be larger and more diffuse than expected, supporting the idea of a partially dissolved or diluted center. Its gravitational field is also lopsided, suggesting that the interior flows and dynamics are far more complex than a simple set of nested layers. This is not just about one planet. The answer is a master key for understanding an entire class of worlds. We have discovered thousands of exoplanets, and a huge fraction are gas giants, many larger than Jupiter and orbiting scorchingly close to their stars. We call them hot Jupiters. Without a clear model for how our own local giant formed and evolved, we cannot accurately interpret the data from these distant cousins. Does a hot Jupiter have a solid core? Did it form farther out and migrate inward, or was it born in that fiery orbit? The structure of Jupiter's interior holds clues to these grand migratory histories. Unlocking the mystery of what lies at the heart of this giant is more than planetary science. It is a test of our ability to comprehend the physics of matter under conditions we can never replicate on Earth. It reminds us that even the largest, most obvious objects in our celestial neighborhood still guard their deepest secrets in a storm of liquid metal. The violent heart of Jupiter is a whisper compared to the cosmic scream of our next mystery. What is the true nature of quasars and active galactic nuclei? These are not simple objects, but the most persistently luminous engines in the known universe, capable of outshining an entire galaxy of 100 billion stars from a region no larger than our solar system. For decades after their discovery, quasars were enigmatic points of radio energy. We now know their terrifying identity. At the center of every quasar, and at the heart of many seemingly normal galaxies, lies a supermassive black hole, millions or even billions of times heavier than our Sun. But a black hole alone is dark. The brilliance comes from its dinner. When vast amounts of gas, dust, and even entire stars are drawn into the black hole's gravitational grip, they do not fall straight in. Instead, they form a whirling, superheated maelstrom called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with a ferocious intensity across the entire electromagnetic spectrum, from radio waves to X-rays. This is an active galactic nucleus. When one is pointed directly at us, its luminosity is boosted by relativistic effects, and we call it a quasar. Yet for all we know, the details remain fiercely debated. The exact physics of the accretion disk itself is a frontier. Is it a smooth, continuous flow, or is it clumpy and unstable? How does material finally cross the event horizon? Even more spectacular are the jets. In many active galaxies, twin beams of charged particles are shot out from the poles at nearly the speed of light, stretching for hundreds of thousands of light years into intergalactic space. These jets are like cosmic blowtorches, carving through the galaxy's own gas and influencing the formation of new stars. But how are they formed? The leading theory involves the black hole's spin and immensely powerful magnetic fields that are wound up by the swirling accretion disk. Like a gigantic natural particle accelerator, these fields can funnel material away from the poles and launch it into the void. The origin and precise structure of these magnetic fields, however, is still a major unsolved puzzle. Understanding these monsters is not just about the black holes themselves. Quasars are fundamental drivers of galaxy evolution. Their radiation and jets can heat up or blow away a galaxy's reservoir of star-forming gas, effectively shutting down the creation of new stars. This feedback process is why we do not see giant galaxies with endlessly forming stars. The quasar at its heart acts as a cosmic regulator, a self-imposed limit on its own growth. Furthermore, because quasars are so blindingly bright, they serve as lighthouses for probing the farthest, earliest reaches of the cosmos. The light from the most distant quasars has been traveling for over 13 billion years, and as it passes through intergalactic clouds of hydrogen, it creates a unique fingerprint in its spectrum. By reading this fingerprint, astronomers can map the large-scale structure of the universe when it was in its infancy. These ancient beacons allow us to witness the epoch when the first galaxies were switching on and the cosmic dark ages were coming to an end. They are both the destroyers and the illuminators of the cosmic landscape, their unresolved fury writing the history of everything around them. These cosmic beacons illuminate the distant past, but another invisible rain carries messages from the present-day violence of the universe. The 13th question asks, what is the origin of ultra-high-energy cosmic rays? These are not rays of light, but atomic nuclei, the hearts of atoms like iron or oxygen, stripped of their electrons and hurled across the cosmos at velocities almost indistinguishable from the speed of light. When one of these microscopic bullets strikes the top of Earth's atmosphere, it unleashes a catastrophic cascade of secondary particles, a sprawling air shower that can rain down over several square miles. The energy packed into a single one of these subatomic specks is staggering, millions of times greater than anything we can produce in our most powerful particle accelerators like the Large Hadron Collider. It is the kinetic energy of a professionally thrown baseball, concentrated into a single atomic nucleus. The existence of such particles is a profound mystery because the universe is a terrible place to accelerate anything to such extremes. Over vast distances, the constant sea of cosmic microwave background radiation, the afterglow of the Big Bang, should act like a thick fog, robbing these nuclei of their energy long before they could reach us. The fact that they do arrive means they must come from relatively nearby in cosmic terms, within a few 100 million light-years of Earth, and they must be born in environments of almost unimaginable fury. Identifying these cosmic accelerators, however, is fiendishly difficult. Unlike light, which travels in straight lines, these charged particles are deflected by the weak but pervasive magnetic fields that fill the space between galaxies. By the time they reach us, their paths are hopelessly scrambled. They point back not to a single source, but to a broad, fuzzy smear of sky. It is like trying to find the origin of a leaf that has been tumbling down a winding river for 1,000 miles. So what cosmic engines are powerful enough to launch them? The prime suspects are the most violent objects we know. Active galactic nuclei with their supermassive black holes and relativistic jets are natural candidates. These jets could act as natural particle accelerators on a galactic scale, channeling matter and energy with forces far beyond anything we can comprehend. Another possibility is the aftermath of a gamma-ray burst, the single most luminous explosion in the universe, thought to accompany the birth of a black hole from a collapsing massive star or the merger of neutron stars. The shockwaves from such an event could, in theory, accelerate particles to these insane energies. More exotic sources have been proposed, including the decay of hypothetical super-heavy dark matter particles from the early universe or cataclysmic events within galaxy clusters. To solve the mystery, we must catch more of these elusive particles, and that is a problem of sheer scale. Because they are so incredibly rare, perhaps only one particle per square kilometer per century strikes the Earth at the very highest energies. You need a detector the size of a small country. Scientists have met this challenge with ingenuity. The Pierre Auger Observatory in Argentina covers 3,000 square kilometers of the Pampas Plains with 1,600 water tanks spaced over a grid. When the cascade of particles from an air shower passes through a tank, it produces a faint blue glow of Cherenkov radiation, which is picked up by sensitive photomultiplier tubes. Meanwhile, telescopes on the site watch for the faint ultraviolet fluorescence the shower produces as it streaks through the night sky. By combining these two methods, the observatory can reconstruct the energy, direction, and type of the primary cosmic ray. Even with this colossal effort, the data remains sparse and the sources elusive. Each ultra-high-energy cosmic ray is a messenger from a place of ultimate violence, carrying a coded letter about the most extreme physics in the nearby universe. But the letter has no return address, and we are only just learning how to read the handwriting. Our galaxy is not adrift in a still ocean. It is racing through the cosmic void at over 600 kilometers per second, pulled by a force we cannot see. This is the 14th mystery. What is the great attractor and what is pulling our galaxy? For decades, astronomers have known that the Milky Way, along with our entire local group of galaxies, is not simply expanding with the universe. We are caught in a specific, powerful current, streaming toward a point in the distant constellation Centaurus. This mysterious focal point of gravity was named the Great Attractor. The problem is, we cannot look directly at it. Our view toward that region of space is completely obscured by the dense plane of our own galaxy, a band of gas, dust, and stars we call the zone of avoidance. It is like trying to see a distant city while standing in a thick, blinding fog. For a long time, the Great Attractor was a ghost, a gravitational signature without a visible source. What could possibly exert such a pull on thousands of galaxies, including our own? The first clues came from painstaking observations that peered through the murk. Using radio and infrared telescopes which can see through interstellar dust, astronomers began to map the hidden structures behind the Milky Way's bulge. They discovered that the Great Attractor is not a single, unimaginably massive object, but rather a colossal concentration of mass, an overdensity on a scale that defies easy comprehension. It is the heart of a vast supercluster of galaxies, a gravitational anchor point for our entire galactic neighborhood. This region, now understood to be part of the even larger Laniakea supercluster, contains the mass of perhaps 100,000 Milky Ways. The pull we feel is the combined gravity of all those galaxies and, more importantly, the immense halo of dark matter that envelops them. The Great Attractor is in essence the deepest valley in the local cosmic landscape, and we are sliding down its slopes. But the story does not end there. Our motion toward the Great Attractor is itself just a component of an even larger flow. We are part of a broader current pulling thousands of superclusters toward an even more massive and distant structure known as the Shapley Attractor, the single greatest concentration of matter in our observable universe. This reveals a cosmos that is not smooth and uniform on the largest scales, but frothy and filamentary, with vast empty voids bordering great walls and knots of galaxies. Our journey is a reminder that we are not passive observers of an expanding universe. We are active participants in a dynamic gravitational dance, tugged by shadows we are only beginning to map. The Great Attractor is not a destination, but a signpost in an unseen topography, pointing toward the hidden architecture of everything. The hidden architecture of the cosmos is traced by more than just gravity's silent pull. Sometimes the universe sends a shout. In 2007, astronomers reviewing old data from the Parkes Radio Telescope in Australia found something that should not have been there. A spike of radio energy so intense it saturated the equipment, lasting just 5 milliseconds. It came from deep space beyond our galaxy, and it carried more energy in its fleeting burst than our Sun releases in 80 years. This was the first recognized fast radio burst, an FRB. Since then, we have detected hundreds of these enigmatic flashes. They are the universe's most brilliant and most baffling radio sirens, appearing randomly across the sky, vanishing in the blink of an eye. The central mystery is what natural engine could possibly produce such a staggering amount of energy in such an impossibly short time. The debate initially split into two camps. The first argued these were cataclysmic, one-time events, the final death cries of extreme objects. A popular candidate was the merger of two neutron stars, the ultra-dense corpses of massive suns. As they spiral together and collide, they could unleash a titanic blast of radiation across multiple wavelengths, including a fleeting, coherent radio scream. Another possibility was an asteroid falling onto a neutron star, the impact vaporizing into a momentary radio fireball. These models made sense. They were cosmic bombs that go off once and are gone forever. Then everything changed. In 2016, astronomers found an FRB that repeated. It was not a one-off explosion, but a source that could flash again and again, sometimes in a frantic, unpredictable pattern. This discovery shattered the simple cataclysm model. You cannot have a star explode multiple times. The repeating bursts pointed to an engine that could survive its own outburst, something with immense magnetic fields or rotational energy that could power multiple events. The prime suspect became a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Think of a magnetar as a cosmic powerhouse wound impossibly tight. A starquake on its crust, a sudden snapping of those magnetic field lines, could theoretically release a focused beam of radio energy in a millisecond flash. We have even detected an extremely bright FRB from within our own galaxy that was linked to a known magnetar, providing the first direct evidence for a possible source. But the story is not so simple. While some FRBs fit the magnetar model, others defy it. We have now localized many bursts to their host galaxies, and they come from all types of environments, young, star-forming galaxies and old, quiet ones. Some repeat with clockwork regularity, others are utterly random. Some are incredibly bright, others faint. This staggering diversity suggests we are not looking at one type of source, but perhaps several. An FRB could be the signature of a young, hyperactive magnetar in a stellar nursery, or an older one flaring in a retired galaxy. Other theories push into even more exotic territory, involving advanced stages of stellar evolution, like the collapse of a supermassive neutron star into a black hole, or interactions of powerful jets with surrounding material. The truth is, no single theory on the table can yet explain the full zoo of FRB behaviors we have observed. Each millisecond flash is a coded message from a distant galaxy, written in a language of pure energy we are still struggling to decipher. They are cosmic telegrams, urgently brief, endlessly mysterious, reminding us that the universe still holds engines of power whose mechanisms we have not yet dreamed of. The fleeting brilliance of fast radio bursts hints at isolated cosmic violence, but step back far enough and a grander, calmer architecture emerges. Our 16th question asks, what is the structure of the universe on the largest scales? If you could view the cosmos from a vantage point billions of light years away, you would not see a random scattering of galaxies. Instead, you would witness a delicate, luminous web, a cosmic spider's silk traced in starlight. Galaxies are not the whole story. They are merely the glittering beads strung along vast, invisible filaments of dark matter. These filaments stretch across hundreds of millions of light years, connecting at dense nodes where immense clusters of thousands of galaxies swarm. Between these threads lie the great cosmic voids, unimaginably empty regions spanning hundreds of millions of light years where few galaxies dare to dwell. This is the cosmic web, the largest structure we know of, and its blueprint was drawn by dark matter's gravity in the first moments after the Big Bang. Tiny quantum fluctuations in that primordial density were stretched to cosmic size by inflation, becoming the seeds for all structure. Over billions of years, gravity amplified these seeds, pulling dark matter and gas into the filaments and nodes, with galaxies forming like dew on this invisible scaffold. This web is the universe's skeleton, and we are mapping it through massive surveys like the Sloan Digital Sky Survey and the upcoming Vera C. Rubin Observatory. By plotting the three-dimensional positions of millions of galaxies, we create a tomographic scan of the cosmos, revealing the filaments and voids in stunning detail. This map is not just for show, it is a forensic tool. By measuring how the web has grown and stretched over cosmic time, we can measure the strength of dark energy, the force that is fighting against gravity's pull. But this magnificent, structured web presents its own profound puzzle, known as the horizon problem. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see a universe that is almost perfectly uniform in temperature. Regions on opposite sides of the sky, which have been separated by over 90 billion light-years since the beginning, have the same temperature to 1 part in 100,000. According to the classic Big Bang model, these regions could never have been in contact. Their light has not had enough time to travel between them to equalize conditions. It is like walking into a vast concert hall and finding every single seat, even those on opposite balconies, at exactly the same comfortable temperature without any heating or cooling system to connect them. How did the universe achieve this stunning homogeneity? The leading and most compelling solution is the theory of cosmic inflation. This proposes that in the first tiny fraction of a second, the universe underwent a period of exponential, faster-than-light expansion. Before inflation, the entire observable universe was smaller than an atom and could easily reach a uniform temperature. Then, inflation blew this tiny, uniform region up to a size larger than our entire observable cosmos, preserving that smoothness while stretching quantum seeds into cosmic hills and valleys. Inflation elegantly solves the horizon problem, but it does more. It predicts the specific pattern of slight variations in the cosmic web we now observe. Our ongoing mapping missions are a test of that prediction. Every new galaxy catalogued is a point in a graph that traces the story of our universe from its first frantic moment to its present grand, webbed expanse, a story whose final chapters are still being written by the unknown nature of dark energy itself. The cosmic web sets the stage, but its greatest marvels are the intricate worlds that form within its threads. Our 17th mystery asks, how do stars and planetary systems actually form? We know the broad strokes. A vast cloud of cold gas and dust collapses under its own gravity, spinning into a disk where a star ignites at the center and planets coalesce from the leftover material. But the devil, as they say, is in the details, and those details are where our textbook understanding breaks down into a series of elegant, unresolved puzzles. Take the very first step, the collapse of a giant molecular cloud. These cosmic nurseries are not serene, they are threaded with powerful magnetic fields. Theory suggests these fields should provide enough support to resist gravity, effectively putting a brake on star formation, yet stars form anyway and in great numbers. So how does the cloud overcome this magnetic barrier? The leading idea is a process called ambipolar diffusion, where neutral gas particles slowly slip past the trapped magnetic field lines. But is this slow leak sufficient, or are there more violent processes at work, like turbulent flows that twist and tangle the fields until they snap? We simply do not know how the magnetic lock is picked. Then there is the problem of spin. As the cloud collapses, it must conserve angular momentum, spinning faster and faster, like a figure skater pulling in her arms. If this process continued unchecked, the forming star would be torn apart by centrifugal force long before it could ignite. Something has to carry that spin away. The answer is thought to be the protoplanetary disk itself and those same magnetic fields, acting as a cosmic brake, transferring angular momentum outward and allowing material to fall onto the growing star. But the precise mechanism of this transfer, whether it is through magnetic winds or spiraling waves in the disk, remains a major unsolved problem in astrophysics. It is the reason our solar system exists, yet we cannot fully replicate the physics in our models. Once the star is forming, the real magic begins in the disk. Here, microscopic dust grains of silicate and ice must somehow stick together to form mountain-sized planetesimals, the building blocks of planets. This is the planetesimal formation problem. The first stage seems straightforward. Gentle collisions allow tiny grains to stick electrostatically, like cosmic dust bunnies. But as these clumps grow to centimeter or meter size, trouble arises. When they collide at higher speeds, they are more likely to shatter than to merge. Even worse, drag from the surrounding gas should cause these pebble-sized objects to spiral inward rapidly, plunging into the central star before they can grow any larger. It is a bottleneck that theories struggle to pass. One compelling solution is the streaming instability. In this model, pebbles drifting inward concentrate into dense filaments under the influence of gas drag. Within these filaments, their collective gravity can rapidly trigger the collapse of a swarm of pebbles directly into a planetesimal tens of kilometers across, bypassing the problematic middle stages entirely. This is where our newest eyes on the universe are transforming the field. The Atacama Large Millimeter Array, ALMA, observes in radio wavelengths, revealing the cold dust and gas in protoplanetary disks with breathtaking clarity. Its images show disks that are not smooth, but intricately structured with bright rings and dark gaps that look like grooves on a cosmic record. These gaps are likely carved by newborn planets, their gravity sweeping their orbits clear. Meanwhile, the James Webb Space Telescope observes in infrared, peering through the dust to see the warmer material and even detecting the chemical signatures of water and organic molecules in these planet-forming zones. Together, they provide a real-time laboratory, but with each stunning observation comes a new puzzle. ALMA has seen disks with multiple, perfectly concentric rings long before planets massive enough to carve them should have formed. Could these rings be caused by other processes, like frost lines where certain materials freeze out, or by subtle instabilities in the disk itself? Webb is finding that the inner regions of disks where rocky planets like Earth form are much more chaotic and turbulent than expected, with material mixing in ways our models do not predict. We are witnessing the blueprint of solar systems being drawn, but we are still learning to read the architect's handwriting. Every newborn star we see is a test case, a chance to solve the riddle of our own origins, piece by elusive piece. Even the most carefully planned voyages can carry home a whisper of the unknown. The 18th question takes us from the grand formation of solar systems to the precise, lonely journeys of our own robotic explorers. What is the nature of the Pioneer anomaly and the flyby anomaly? For decades, scientists have tracked our spacecraft with exquisite precision, using the Doppler shift of their radio signals to measure their speed to within a fraction of a millimeter per second. And in that pristine data, they found tiny, stubborn discrepancies that should not exist. The Pioneer anomaly was discovered when analysts looked at the trajectories of the Pioneer 10 and Pioneer 11 probes launched in the 1970s. As these veteran spacecraft sailed beyond the orbits of the outer planets on their way to interstellar space, they were experiencing a constant, minuscule deceleration toward the Sun. It was as if a faint, unseen hand was gently tugging them backward, a force about 10 billion times weaker than the gravity we feel on Earth's surface. But according to Newton and Einstein, once a probe escapes the Sun's gravity, its speed should remain constant, coasting on forever. This tiny drag was a profound puzzle. Was it a sign of new physics, perhaps a modification to Einstein's theory of gravity on very large scales, or an effect of dark matter? The mystery lingered for years, a tantalizing crack in our understanding. The scientific community, however, is a relentless detective. Teams began to scrutinize every possible mundane explanation. The leading suspect was thermal radiation pressure. The Pioneer probes were powered by radioactive plutonium, and the heat from that power source was emitted anisotropically, meaning not perfectly evenly in all directions. More heat was radiating from the back of the spacecraft than the front. Photons, though massless, carry momentum. If more photons were pushing off the back of the probe than the front, it would create a tiny net force slowing the craft down, exactly like a faint, continuous rocket thrust in reverse. Through painstaking computer modeling that reconstructed the spacecraft's complex heat distribution and emission, researchers finally concluded that this thermal effect could account for almost the entire anomalous deceleration. The Pioneer anomaly, once a beacon for new physics, was likely explained by the simple, forgotten warmth of its own nuclear battery. But the story of anomalous trajectories does not end there. A related and still unresolved mystery is the flyby anomaly. When spacecraft perform a gravity-assist maneuver, swinging past Earth to gain a speed boost for journeys to the outer solar system, their final velocity is predicted with incredible accuracy. Yet on several occasions, like with the Galileo, Near, and Rosetta missions, the spacecraft emerged from the flyby with a tiny, unexpected change in speed, a difference of a few millimeters per second. This is not a constant drag like Pioneer, but a single, precise jump that our models fail to predict. The possible explanations range from the subtle to the revolutionary. Could it be an unaccounted-for effect of Earth's atmosphere, even at high altitudes, or irregularities in our planet's gravitational field? Perhaps it is a flaw in how we model the Doppler effect itself at such extreme precision. Or, as some physicists still speculate, could it be a hint of something deeper, like a coupling between a spacecraft's rotation and Earth's gravity, an effect not included in standard general relativity? To date, no single explanation has gained universal acceptance, and the flyby anomaly remains an open case file. These anomalies, one largely solved and one still mysterious, are not failures of science. They are its greatest strength. They represent the ultimate stress test of our theories, conducted across billions of miles of empty space. When our predictions are this precise, even a discrepancy the width of a human hair, measured across the solar system, becomes a glaring clue. It teaches us that the universe often whispers its secrets first, in the faint, stubborn drift of a silent probe against the starry dark. The precise trajectories of our spacecraft test the laws we think we know, but those laws themselves are built on a set of numbers that seem suspiciously perfect. This is the 19th great mystery. Are there other universes with different physical constants? The strength of gravity, the mass of an electron, the force that binds atomic nuclei. These are not derived from any deeper principle in our current theories. They are inputs, knobs set to very specific values, and if any one of those knobs were turned even a fraction, the universe as we know it would vanish. If the strong nuclear force were slightly weaker, protons and neutrons would not stick together, and no complex atoms beyond hydrogen could form. If it were slightly stronger, stars would burn their fuel in a furious flash, leaving no time for planets or life to evolve. If the cosmological constant, the energy of empty space, were larger by a minuscule amount, the universe would have blown itself apart before galaxies could form. This eerie perfection is known as the fine-tuning problem. It feels as if the cosmos was engineered for life, a notion that has sparked endless philosophical and scientific debate. One compelling answer is the anthropic principle. In its simplest form, it states that we can only observe a universe capable of producing observers like us. It is a selection effect, not an explanation. Of course, we find ourselves in a universe with the right constants, because in a universe with the wrong ones, no one would be here to wonder about it. This can feel like a tautology, a fancy way of saying we got lucky. But when combined with the concept of a multiverse, it transforms from a philosophical shrug into a powerful scientific framework. If a vast multiverse exists, where every possible set of physical constants is realized in some bubble or branch, then it is no surprise that we find ourselves in one of the rare, hospitable bubbles. We are not the purpose of the cosmos, we are simply a statistical inevitability in an infinite ensemble of realities. In this view, fine-tuning is not evidence of design, but of a staggering cosmic lottery where our ticket just happened to be the winning one. The multiverse provides a potential explanation, but it also raises a profound challenge. If every possible universe exists, then our specific, seemingly special set of constants is rendered utterly ordinary. The quest for a fundamental theory that predicts why these numbers must be what they are is potentially abandoned. some physicists find this deeply unsatisfying. They argue that the multiverse is a retreat, a way to explain away a problem we have not yet solved. The alternative is to seek a theory so complete, so elegant, that it leaves no room for arbitrary numbers. The dream of a final theory would derive all constants from pure mathematics and geometry, showing that our universe is not one possibility among infinite others, but the only one logically consistent. String theory initially promised this, but instead revealed a landscape of perhaps 10 to the 500 possible vacuum states, each with its own laws, ironically giving birth to the modern multiverse concept. So we are left with two starkly different visions of reality. In one, we live in a unique cosmos whose laws are inevitable and waiting to be discovered by a theory of everything. In the other, we inhabit a single neighborhood in an infinite cosmic metropolis, where the local bylaws are random and ours just happen to allow for trees and telescopes and questioning minds. Both paths lead to a humbling truth that the very rules of our reality, the stage upon which every cosmic drama plays out, remain one of the deepest and most consequential puzzles of all. The constants of reality may be fixed, but the moon, our silent companion, is not as static as it seems. For centuries, sharp-eyed observers have reported strange, fleeting events on its dusty face, brief flashes of light, sudden patches of glowing haze, or local obscurations that dim the terrain. These are transient lunar phenomena, or TLPS, and they remain one of the solar system's most persistent and puzzling observational mysteries. The reports are credible and span the globe, from amateur astronomers with backyard telescopes to the astronauts of the Apollo program, who were specifically asked to watch for them. The events themselves are maddeningly brief, often lasting just seconds or minutes, and they are never in the same place twice, making them nearly impossible to predict or study in detail. So what could possibly be causing these ghostly flickers on a world we thought was geologically dead? The leading suspect is outgassing. The moon's interior is not completely cold. Radioactive decay provides a faint warmth, and there could still be pockets of trapped volatile gases like radon or argon from its ancient volcanic past. If a subsurface seal were to crack, perhaps due to the slight tidal flexing from Earth's gravity, a puff of this gas could escape. Sunlight hitting the escaping dust and gas could make it glow briefly or scatter light in a way that looks like a hazy patch. Another straightforward explanation is meteorite impacts. The moon has no atmosphere to burn up incoming space rocks, so even small pebbles strike the surface at tremendous speeds, creating instant tiny flashes of light as they vaporize on impact. Networks of telescopes now constantly monitor the moon for these impact flashes, and they are common. But not all reported TLPS match the profile of a simple impact. Some are prolonged glows or dusky red colorations that last too long. Could electrostatic phenomena be at play? The lunar surface is a realm of extreme static electricity. Charged by the solar wind and ultraviolet light, the fine dust can levitate and move in strange ways. Perhaps large-scale electrostatic discharges, like miniature lightning in the dust, could create sudden, localized brightening. Then there is the moon's own internal rumble. Moonquakes detected by seismometers left by Apollo astronauts still occur deep within the crust. While far weaker than Earth's quakes, they could theoretically trigger small avalanches on crater walls, kicking up clouds of dust that catch the sunlight for a brief moment before settling. The challenge is that each of these explanations fits some events, but none fits all of them. Confirming that some TLPS are caused by internal outgassing would be revolutionary. It would mean the moon is not a completely inert fossil. It would suggest a subtle, ongoing geological activity, a world that still breathes faintly, releasing whispers of its ancient history into the vacuum. This changes the moon from a static museum piece into a dynamic world with a slow, hidden heartbeat, a reminder that even the familiar face in our night sky still holds onto its secrets, revealed only in fleeting, enigmatic winks. That faint, flickering moon is a world of unresolved whispers, but one signal from deep space arrived not as a whisper, but as a shout. In the summer of 1972, a radio telescope at Ohio State University known as the Big Ear was engaged in a patient, systematic search. It was listening for any narrowband radio signal, a focused spike at one specific frequency, that could not be explained by natural astrophysics or human technology. For months, the data printer churned out pages of numbers and symbols, a monotonous record of cosmic static. Then, on August 15th, volunteer astronomer Jerry Amon was reviewing the latest printout. His eyes scanned a column of alphanumeric codes representing signal intensity. Most entries were a 1 or a 2, but one sequence corresponding to a frequency near the hydrogen line at 1420 MHz leapt off the page. The characters read 6EQUJ5. In the notation used, letters represented values from 10 upward. This sequence meant a signal intensity that jumped from background noise to 30 times louder, held that peak, and then faded away. Amon circled the sequence in red pen and wrote a single, emphatic word in the margin. Wow, the wow signal was born. Everything about it was tantalizing. It was a strong, narrowband signal, precisely the kind a deliberately broadcast beacon would produce. It came from a region in the constellation Sagittarius with no obvious stars or planets. Most compellingly, it lasted 72 seconds, which was exactly the duration the Big Ear telescope could observe a fixed point in the sky due to Earth's rotation. The signal rose and fell in a perfect curve, matching the telescope's window on that patch of sky. It was as if someone had aimed a cosmic flashlight directly at us, turned it on as we rotated into view, and turned it off as we rotated away. For a brief, electrifying moment, it looked like the discovery humanity had dreamed of, and then nothing. Despite dozens of follow-up searches by the Big Ear and other observatories over the decades, the signal never repeated. Not once, it remains a solitary, brilliant blip in the archives. The hunt for an explanation has been exhaustive. Could it have been a secret military transmission? Unlikely, as that frequency is internationally protected for astronomy, and no known human technology at the time matched its specific profile. Was it a reflection off a piece of space debris? The signal's characteristics make that improbable. In recent years, a hypothesis pointed to comets. Two comets not known in 1972 were in the general area of the sky at that time. Could the signal have been caused by a cloud of hydrogen gas released from one of them? While intriguing, this explanation has been largely dismissed by astronomers. The comets were too far from the precise line of sight, and the hydrogen line is a common natural emission, but the WOW signal was uniquely powerful and narrow, unlike the broad emissions from a diffuse cometary cloud. So the mystery endures. The WOW signal stands alone as the best candidate we have ever recorded for a potential extraterrestrial transmission. It passed every initial test for an artificial interstellar beacon. Yet its singular nature is its greatest frustration and its deepest intrigue. In science, one data point is a curiosity, a story without a second chapter. It is the ghost in the machine of the cosmos, a 72-second hello that left behind only a profound, echoing silence and a question mark written in red ink. A solitary star over 1,000 light-years away refuses to follow the rules. Catalogued as KIC 8462852, but better known as Tabby's star, it behaves like nothing else in our galaxy. Discovered by citizen scientists in the Planet Hunters project who were sifting through data from NASA's Kepler telescope, this star's light curve told a story of chaos. Kepler's mission was to find planets by spotting the gentle, periodic dips in starlight that occur when an orbiting world crosses its sun's face. These dips are predictable and small, typically less than 1%. Tabby's star did something else entirely. It exhibited deep, irregular dimming events, sometimes plunging in brightness by a staggering 22%. These were not the tidy shadows of planets. They were monstrous, jagged eclipses that lasted for days or weeks with no discernible rhythm. The star would also exhibit a long-term, secular dimming, fading by about 3% over the century of observations we have. This was not an instrument error. It was a real astrophysical phenomenon screaming for an explanation. Theories erupted, ranging from the plausible to the spectacular. The first natural explanation was a colossal swarm of comets, perhaps a family of icy bodies shattered by a close encounter, were trailing vast clouds of dust and debris in a highly elliptical orbit around the star. As this fragmented swarm passed in front, it could block varying amounts of light. While this fit some of the irregularity, it strained to explain the sheer depth of the dimming or the century-long fade. Then came the idea that shook the world, the alien megastructure hypothesis. In the 1960s, physicist Freeman Dyson speculated that a sufficiently advanced civilization would eventually need to capture nearly all the energy output of its star. They might construct a vast swarm of orbiting collectors, a Dyson swarm, that would gradually encase the star and irradiate its energy as waste heat in the infrared. Tabby's star, with its bizarre, non-periodic and extreme dimming, seemed to some like a candidate for a partially built, clumpy Dyson swarm under construction. It was a hypothesis born of pure imagination, but it fit the data in a way no natural model perfectly did at the time. For a moment, the world looked at a flickering dot and wondered if we were seeing the shadows of a civilization. Science, however, is a process of patient interrogation. Follow-up studies across the electromagnetic spectrum began to paint a more detailed, if still mysterious, picture. The key clue came from spectroscopy, analyzing how different colors of light were being blocked. If the dimming were caused by solid objects like megastructures or planetesimals, they would block all wavelengths of light equally. But observations showed the star dimmed more in blue light than in red light. This is the classic signature of dust, tiny particles smaller than a grain of sand that scatter shorter blue wavelengths more effectively. The culprit, therefore, was not solid panels or planets, but uneven clouds of fine, cosmic dust passing in front of the star. This was a major pivot away from the extraordinary, back toward natural astrophysics. The latest data suggests a complex, evolving dust environment, possibly from the breakup of a giant planet or a series of catastrophic collisions in a rocky asteroid belt, creating a chaotic cloud of debris on a highly eccentric orbit. The long-term fading could be from a vast, diffused disk of dust slowly drifting into our line of sight. Yet naming the culprit as dust does not solve the mystery, it merely refines it. The origin of that dust is profoundly puzzling. What event could create such an immense, clumpy, and long-lasting cloud? The dust must be replenished, as radiation pressure from the star should blow tiny particles away relatively quickly. This implies an ongoing, violent process. Furthermore, the dust does not behave like the smooth rings of Saturn. It is lumpy and opaque in strange patches. The star itself is also unusual, exhibiting rapid fluctuations that suggest it is more active and unstable than a star of its type should be. Perhaps we are witnessing the aftermath of a cosmic collision on a scale we have never seen, or observing a rare phase of stellar evolution where a star is violently shedding material and reshaping its planetary system. Tabby's star remains a landmark case. It is a testament to how citizen science can flag the one anomaly in a mountain of data that professional astronomers might overlook. It shows how a single, stubbornly weird data point can force us to question our assumptions, from comet swarms to the limits of imagination itself. The megastructure hypothesis, while likely wrong, served a vital purpose. It reminded us that the universe is under no obligation to be boring. The true answer is still hidden within those chaotic shadows, a reminder that sometimes the most exciting discovery is not an answer but a better, more bewildering question. Far beyond the last icy orbits of Neptune, our solar system does not simply fade into the dark. It is girded by a vast, donut-shaped reservoir of frozen leftovers known as the Kuiper Belt. Here, worlds like Pluto and Eris drift in a deep freeze that has lasted since the dawn of the Sun. But this belt holds a sharp and puzzling boundary, a feature astronomers call the Kuiper Cliff. Around 50 astronomical units from the Sun, which is 50 times the Earth-Sun distance, the population of these icy objects seems to plummet. It is as if you were walking through a forest that suddenly and definitively gives way to an empty plain. This abrupt edge was not predicted by our standard models of solar system formation. The primordial disk of material from which the planets coalesced should have extended much farther out, tapering off gradually. So what or who cleaned out the neighborhood beyond 50O? One of the most dramatic explanations points to the gravitational hand of an unseen giant. This is the Planet 9 hypothesis. The idea is that a planet, perhaps 5 to 10 times the mass of Earth, orbits the Sun on a highly elliptical path hundreds of O away. During its long, slow swings through the outer solar system, its immense gravity could have shepherded the orbits of countless Kuiper Belt objects, either flinging them inward toward the Sun, outward into interstellar space, or tilting their orbits into the strange, clustered alignments we see today. In this scenario, the Kuiper Cliff is the edge of a pasture that was cleared by a wandering, unseen shepherd. The gravitational evidence for this planet is circumstantial but compelling, based on the peculiar, clustered orbits of a handful of extremely distant objects. Yet, after years of searching, no direct observation has confirmed its existence. A second, less exotic theory looks to a known culprit from the past, Neptune. Our current best model of the early solar system, the NICE model, suggests the giant planets did not form in their current positions. They migrated. Neptune, in particular, is thought to have formed much closer to the Sun and then drifted outward. As it did, its gravity would have scattered the primordial disk of icy bodies, throwing many into the inner solar system to bombard the young planets, while pushing a concentrated population of survivors into resonant orbits just beyond its own path. This migration could have created a sharp outer edge to the belt, like a snowplow piling up a ridge of snow at the end of its path. But could Neptune's influence truly explain such a definitive cutoff so far away? Some simulations suggest it might not be enough, leaving room for other possibilities. The third, and perhaps most humbling, explanation is that the cliff is an illusion of our own limitations. Our surveys of the distant Kuiper Belt are incredibly difficult. Objects that far out are faint, receiving only a whisper of sunlight, and they move very slowly against the starry background, making them hard to distinguish. It is possible that beyond 50O, there exists a second, more distant population of objects that are simply too dark and too slow for our current telescopes to easily find. We might be standing at the edge of a lighted circle, proclaiming the world ends here, while just beyond our lamplight, an entire unseen continent stretches into the dark. Each of these answers tells a different story about our solar system's violent youth. A lurking planet 9 speaks to a dramatic, chaotic rearrangement we have yet to fully map. Neptune's migration paints a picture of a dynamic, evolving architecture shaped by gravitational dances billions of years ago, and an observational illusion reminds us that our knowledge is always bounded by the light we can collect. The Kuiper Cliff is more than a curiosity. It is a fossilized edge from the era of planet building, and deciphering its origin will rewrite the final chapter of how our celestial neighborhood came to be. Magnetic fields are the silent, invisible architecture of the cosmos. They thread through the spiral arms of galaxies, guide the collapse of stellar nurseries, and sculpt the jets screaming from black holes. We even find their faint imprint in the vast, empty voids between galaxy clusters. For objects like Earth or the Sun, we have a compelling explanation called the dynamo theory. Inside our planet's molten iron core, convective currents of electrically conducting fluid, twisted by Earth's rotation, act like a giant electrical generator. This self-sustaining dynamo amplifies and maintains our protective magnetic shield. A similar process churns within stars, but this elegant answer only pushes the mystery one step back. A dynamo cannot create a magnetic field from absolute zero. It can only amplify a pre-existing one. It needs a seed. So where did the very first magnetic fields in the universe come from? This is a profound chicken and egg problem. The first stars and galaxies could not have formed without magnetic fields to help dissipate heat and angular momentum from collapsing gas clouds. Yet those first stars and their dynamos are supposed to be the very sources of those fields. Something had to plant the first seeds in the primordial darkness long before any star ever shone. The search for an answer takes us to the universe's first moments, a seething plasma of particles and radiation. In that frantic, hot soup, even tiny effects could have been stretched to cosmic significance. One possibility involves the Biermann battery effect, a process where pressure and density gradients in a plasma that is not perfectly uniform can spontaneously generate weak electric currents and thus magnetic fields. In the early universe, shock waves from the first gravitational collapses or from violent phase transitions could have created just the right conditions for this cosmic battery to switch on, producing the faintest of magnetic whispers. Another theory looks to the fundamental forces themselves. In the extreme energies of the universe's first fraction of a second, the electromagnetic and weak nuclear forces were unified. As the cosmos expanded and cooled, it underwent a phase transition, much like water freezing into ice. This sudden change in the state of the vacuum could have created defects, cracks in spacetime, that left behind trapped magnetic energy as relics. These primordial fields, born from the splitting of the forces themselves, would then be woven into the fabric of the expanding universe. A more exotic idea involves the elusive neutrino. If these ghostly particles had even a tiny magnetic moment, a slight asymmetry in their spin as they streamed through the early plasma could have generated large-scale currents, seeding magnetic fields on the scale of galaxy clusters. The challenge is that these early seed fields would have been incredibly weak, billions of times fainter than Earth's field today. Detecting their fossil imprint is one of the great quests of modern cosmology. Astronomers search for their signature in the subtle polarization of the cosmic microwave background, or in the way they might twist the light from the most distant quasars. Finding that fossil would be like discovering the signature of the universe's first spark, the initial stroke that magnetized all of creation, setting the stage for every star and galaxy to come. The smooth cosmic web we see today was born from a storm of quantum chaos. To understand the universe's first instant, we must face a theoretical collision of titanic proportions. Our 25th question asks, how do cosmic inflation and quantum mechanics unify? These are the two most successful frameworks in all of physics, yet they describe reality in languages that are fundamentally, perhaps irreconcilably, foreign to one another. Cosmic inflation governs the unimaginably large, describing how the entire cosmos expanded from a subatomic speck to a macroscopic universe in a fraction of a second. Quantum mechanics governs the unimaginably small, the probabilistic, fuzzy world of particles and waves. Merging them is the ultimate goal of a theory of quantum gravity, and without it, the story of the Big Bang has a missing first sentence. The problem begins with the measurement problem, a core paradox in quantum mechanics. In the quantum realm, a particle does not have a definite property like position until it is observed or measured. Before measurement, it exists in a superposition of all possible states, described by a mathematical entity called the wave function. The act of observation somehow collapses this wave function into a single, definite reality. This works in a lab where we have an experiment, an experimenter, and an outside world. But apply this logic to the entire universe and you hit a wall of absurdity. Who was the observer at the Big Bang? What apparatus measured the infant cosmos to collapse its wave function into the reality we see? There was no outside, no separate observer. The universe was, by definition, everything that existed. This leads to the profound concept of the wave function of the universe. In this view, the entire cosmos began as a quantum fluctuation, a ripple in the fabric of nothingness, existing in a superposition of all possible initial states. But without an external observer, how did it pick the specific history that led to us? Some interpretations, like the many worlds interpretation, offer a dizzying answer. It suggests the wave function never collapses. Instead, at that first moment, every possible outcome of that quantum fluctuation became real, each giving birth to its own separate, branching universe. Our reality, with its specific laws and constants, is just one thread in an infinite tapestry of all possible cosmoses. Inflation then becomes a quantum process, a mechanism that takes a tiny quantum seed and stretches it into a vast classical universe. But this is where the languages clash violently. Inflation relies on Einstein's theory of general relativity, which treats spacetime as a smooth classical stage. Quantum mechanics insists that at the tiniest scales, that stage must be frothy, chaotic, and discontinuous. At the moment of the Big Bang, when the universe was smaller than a single atom, these two descriptions must merge. Our current equations simply break down. We need a theory that can describe gravity itself in quantum terms, a theory of quantum gravity. This is the holy grail of modern physics. Leading candidates like string theory or loop quantum gravity attempt to rewrite the rules, suggesting that space and time are not fundamental, but emerge from something deeper, like vibrating strings or a network of quantum loops. In these frameworks, the Big Bang might not be a true singularity, but a bounce from a previous contracting phase or a transition from a timeless, spaceless state. Until we have such a theory, the very first instant of creation remains shrouded in a quantum fog. We can describe what happened a tiny fraction of a second after the beginning, but the moment of beginning itself is a blank page, waiting for a new physics to write the first word. Every second, trillions of ghostly particles stream through your body, leaving not a single trace. These are neutrinos, and their very existence challenges our most basic understanding of the universe. They are the most abundant massive particles in the cosmos, born in the nuclear hearts of stars, in the cataclysms of supernova, and in the first second of the Big Bang itself. Yet they are defined by what they do not do. Neutrinos are electrical phantoms with no charge, and they interact with ordinary matter only through the weak nuclear force and gravity. This makes them nearly impossible to catch. To even have a chance, scientists build colossal detectors deep underground, in abandoned mines or beneath mountains, shielded from cosmic rays. They fill these caverns with ultra-pure water or liquid scintillator and wait. When on rare occasion a neutrino does strike an atomic nucleus, it produces a faint flash of light, a whisper of its passage. Their reluctance to interact is why we call them ghost particles, but their elusive nature hides three profound mysteries that could rewrite the laws of physics. The first mystery asks a bizarre question: are neutrinos their own antiparticles? For every other particle we know, like the electron, there is a distinct antimatter counterpart, the positron. But a theory proposed by physicist Eta Majorana suggests that neutrinos could be an exception, that a neutrino and an antineutrino are actually the same entity. If this is true, it would be a revolution. It would mean that under certain conditions, a neutrino could annihilate itself, a process that could have been crucial in the early universe. This property, called Majorana nature, is a leading candidate for explaining the matter-antimatter asymmetry. If neutrinos are Majorana particles, they could have triggered processes that favored the creation of matter over antimatter in the universe's first moments, solving the mystery of why we exist at all. The search for this is embodied in experiments hunting for an ultra-rare nuclear process called neutrinoless double beta decay. If observed, it would be the smoking gun, proving the neutrino is its own antiparticle. The second mystery is deceptively simple. What is the absolute mass of a neutrino? We know from other experiments that neutrinos have mass, but it is vanishingly small, millions of times lighter than an electron. We do not, however, know the exact number on the scale. This is not a minor detail. Neutrinos are so abundant that their collective mass could shape the fate of the cosmos, influencing how galaxies cluster and how the universe expands. Pinpointing this mass is a monumental technical challenge, involving studying the precise endpoint of the energy spectrum in nuclear decays, or measuring the large-scale structure of the universe with extreme precision. The third mystery is perhaps the strangest, the phenomenon of neutrino oscillation. Neutrinos come in three types or flavors: electron, muon, and tau. As a neutrino travels through space, it does not stay as one flavor. It morphs, oscillating between all three identities. This is only possible if neutrinos have mass, a discovery that earned the Nobel Prize. But the pattern of these oscillations is not what our standard model predicts. There is a mismatch, an anomaly in the data suggesting a missing piece. Some theorists propose a fourth, sterile neutrino, a particle that interacts only through gravity, not even the weak force. Its existence would be a portal to physics far beyond our current understanding. Solving these three interlocking puzzles is more than particle physics. It is archaeology of the cosmos. Neutrinos from the Sun tell us about fusion in its core. Neutrinos from a supernova that reached Earth in 1987 gave us a real-time alert of a star's death, and the relic neutrinos from the Big Bang, which fill every cubic inch of space, are a fossil snapshot of the universe 1 second old. To understand these ghosts is to read a hidden history of everything, written in particles that pass through walls, planets, and us, as if we were not even there. The cosmic microwave background is the oldest photograph of our universe, a snapshot from when it was just 380,000 years old. This faint, cold glow, bathing all of space at just a few degrees above absolute zero, is the afterglow of the Big Bang itself. For cosmologists, it is a treasure map, its subtle temperature variations revealing the seeds of all future galaxies. Yet within this seemingly uniform tapestry, there is a pattern that makes scientists profoundly uneasy, a series of large-scale alignments and asymmetries that have earned a dramatic nickname, the axis of evil. It is not a malevolent force, but a statistical anomaly so strange it threatens a cornerstone of modern cosmology. The cosmological principle states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks the same in every direction. There should be no special axis, no preferred left or right, no grand up or down. The CMB data, however, whispers otherwise. When scientists analyze the temperature fluctuations across the sky, they find that the hot and cold spots are not distributed with perfect randomness. Instead, they appear to align along a particular plane in space, a kind of cosmic equator. Even more unsettling, there is a significant asymmetry between the two hemispheres of this alignment. One half of the sky shows larger temperature variations than the other. It is as if you painted a room with meticulous care, only to step back and see that all the brushstrokes on one wall slant in the same direction, and the paint on the ceiling is a completely different shade. The implications are staggering. If this axis is real and not an illusion, it suggests the universe has a handedness, a preferred direction imprinted at its birth. This could mean the cosmos is not isotropic, that the Big Bang itself was not perfectly symmetric, or that our universe is part of a larger anisotropic structure. Some have even speculated it could be a bruise, a relic of a collision with another universe in the multiverse. the scientific community has pursued every possible mundane explanation first. Could it be a subtle contamination from our own galaxy? The Milky Way's dust and magnetic fields do emit foreground radiation that must be meticulously subtracted from the SIM signal. Teams have analyzed the data from multiple satellites, from COBE to WMAP to Planck, using different methods to strip away this local interference. The peculiar alignments persist. Could it be a statistical fluke? When you have millions of data points, some strange correlations are bound to appear purely by chance. But the odds of the axis of evil appearing randomly are extremely low, perhaps less than 1 in 1,000. In science, that is a red flag, not a dismissal. The most unsettling possibility is that it is a genuine feature, a crack in the cosmological principle. If the universe has a preferred axis, then our entire standard model of cosmology, which assumes perfect large-scale uniformity, requires a fundamental rewrite. It would mean we do not occupy a typical place in a typical universe, and the laws of physics themselves might vary along different cosmic sightlines. This is not a mystery we can solve with better telescopes alone. It is a puzzle written into the first light of creation, asking us if our most cherished assumption about the cosmos, its essential fairness and sameness, is nothing more than a beautiful, broken idea. The moon's serene face is a mask for a violent past. Our 28th question asks, what is the origin of the moon? For generations, the leading answer has been a cataclysm of almost unimaginable scale, the giant impact hypothesis. In this story, the early Earth, still molten and forming, shared its orbit with a Mars-sized protoplanet named Theia. Inevitably, their paths crossed. Theia struck our young world a glancing but devastating blow. The impact was not a simple collision, it was a merger of fire and rock. Theia's core sank into Earth's mantle, while a colossal plume of vaporized rock and molten debris was blasted into orbit. This incandescent cloud of shattered planet quickly coalesced under its own gravity, cooling into the sphere we see today. It is a beautiful, dramatic narrative that explains so much: the moon's lack of a substantial iron core, its similar age to Earth, and the angular momentum of the Earth-Moon system. For decades, it was the textbook answer, but science advances by finding the cracks in its own stories, and the moon's origin story has developed a significant fault line. The problem lies in the rocks. When Apollo astronauts brought lunar samples home, geochemists expected to find a distinct fingerprint, a signature of the alien world Theia. Instead, they found something deeply puzzling. The isotopic compositions of oxygen, titanium, tungsten, and other elements in moon rocks are virtually identical to those found in Earth's mantle. It is as if the moon was made from the exact same material as our planet's outer layer. This is extraordinarily difficult to reconcile with a giant impact from a separate, independently formed planet. Theia, having formed in a different part of the solar system, should have had a markedly different isotopic signature. So why does the moon look so much like a piece of Earth? This isotopic crisis has forced planetary scientists back to the drawing board, refining the impact model in radical ways. One alternative is the hit-and-run scenario. Perhaps Theia was much larger than Mars-sized, and the collision was even more violent and high-speed. In this model, Theia would have been almost completely vaporized and mixed with a huge portion of Earth's mantle, creating a well-mixed cloud of debris from which both bodies reformed. The Earth and Moon we know today would be the children of that total merger, explaining their chemical twinship. An even more exotic idea discards the notion of a solid impactor entirely. Instead, scientists propose a structure called a synestia. Imagine the early Earth spinning so rapidly from previous collisions that it is no longer a solid sphere, but a donut-shaped mass of vaporized rock, a seething, superheated disk with a central condensation. If another body struck this whirling inferno, it would have blended perfectly into the chaotic mix. The Moon would then condense from the outer edges of this common pool of material, while Earth reformed from the center. In this view, Earth and the Moon are not parent and child, but siblings born from the same catastrophic event. Each model tries to save the core idea of a giant impact while accounting for the stubborn chemical evidence. Yet each introduces new complexities. A hit-and-run impact requires very specific, fine-tuned conditions. A synestia is a theoretical state we have never directly observed. The debate is far from settled, and it is fueled by every new lunar sample and computer simulation. The mystery of the Moon's birth is not some distant abstraction. It is written in the rocks beneath our feet and in the pale light above us. Solving it is key to understanding our own planet's violent adolescence, the frequency of similar moons around other worlds, and the very processes that build rocky planets. Our closest companion, the anchor of our tides and the muse of our poetry, remains a world with an origin story still being written, a reminder that even the most familiar faces can hide the most profound and unresolved secrets. The universe's first recipe book is written in the lightest elements, and one ingredient is stubbornly missing. In the furnace of the Big Bang's first few minutes, a process called Big Bang nucleosynthesis forged the primordial atoms. Hydrogen fused into helium with trace amounts of deuterium and lithium stamped into existence before the expanding cosmos cooled and froze these ratios forever. We can calculate with stunning precision how much of each element should have been created. For deuterium and helium, the predictions match the ancient, pristine gas we observe in the far reaches of space. But for lithium, the third lightest element, the math is catastrophically wrong. The predicted amount of lithium-7, the main stable isotope, is about 3 times higher than what we actually find in the atmospheres of the oldest stars in our galaxy. This mismatch is not a small rounding error. It is a glaring discrepancy known as the lithium problem, and it threatens our entire understanding of the universe's first 3 minutes. To grasp why this is so troubling, think of those ancient stars as cosmic time capsules. Born from nearly pure Big Bang material, their outer layers should preserve the pristine chemical signature of the infant cosmos. Astronomers use powerful telescopes to dissect the light from these ancient suns, reading the faint absorption lines that reveal their chemical composition. Star after star, in galaxy after galaxy, tells the same story: lithium is scarce. It is as if we opened a perfectly preserved can of soup from 100 years ago and found one key ingredient was only 1/3 of the amount the original recipe called for. The recipe itself, the standard model of Big Bang nucleosynthesis, is built on the well-tested laws of nuclear physics and the known conditions of the early universe. If the predictions are so precise for deuterium and helium, why does lithium break the pattern? Scientists are probing for the error in 3 distinct places: the nuclear physics, the stars themselves, and the very laws of the cosmos. The first possibility is that we have misunderstood the nuclear reactions that made lithium. Perhaps there is an unknown nuclear reaction pathway in the early universe that destroyed lithium-7 as quickly as it formed. Researchers have scrutinized the cross-sections, the probabilities, of every conceivable reaction involving lithium, beryllium, and boron. Could lithium have been transformed into something else by colliding with a stray proton or neutron? So far, tweaking the known nuclear physics within reasonable limits has not closed the gap. The second, and perhaps most likely, explanation lies not in the creation but in the destruction. Maybe the ancient stars are not perfect time capsules after all. Even these venerable suns have turbulent interiors, processes like diffusion, where heavier elements slowly sink inward over billions of years, could have drained lithium from the observable surface layers down into the stellar core, where it is burned as fuel. Or perhaps these stars were born with the correct amount of lithium, but their powerful magnetic fields or unusual rotation churned and destroyed it early in their lives. The challenge is that we need a stellar process efficient enough to destroy exactly 2/3 of the lithium in every single ancient star we look at, a universal stellar vandal that left no other obvious trace. The third possibility is the most radical, that we need new physics to explain the conditions of the early universe itself. Could exotic particles, like certain types of dark matter, have been present during those first minutes? If these particles decayed or interacted with the primordial plasma, they could have altered the density and temperature at just the right moment to suppress lithium production. Alternatively, perhaps the constants of nature, like the strength of the gravitational force, were slightly different in that extreme environment. Any such discovery would shatter our current models and open a window into physics far beyond the standard model. The lithium problem is more than a chemical accounting error. It is a direct observational test of our cosmology, a fossilized clue from the universe's infancy that something in our story is incomplete. Whether the answer lies in stellar cauldrons or in the shadow of new particles, solving it will force us to rewrite a critical page in the first chapter of everything. Our final question takes us to the very bedrock of reality. Is space-time fundamentally smooth or granular? We have journeyed through the cosmos from dark matter to the Big Bang, but all those mysteries exist upon a single stage, the four-dimensional fabric of space and time. Einstein's general relativity describes this stage as a smooth, continuous sheet that can bend and warp. But our other great theory, quantum mechanics, insists that everything in nature is ultimately grainy, made of discrete packets like photons or electrons. So which is it? Is the fabric of the universe a seamless cloth, or is it a cosmic tapestry woven from indivisible threads? The quest to answer this is the search for a theory of quantum gravity, and it may require us to abandon our most basic intuition about the nature of reality itself. The clash becomes unavoidable at an unimaginably tiny scale called the Planck length. This is about 1/trillionth of a trillionth the diameter of a proton. At this scale, the smooth geometry of general relativity is predicted to break down into a seething, chaotic froth. This is quantum foam, a concept where space-time itself is not stable. Microscopic wormholes might blink in and out of existence, and the very concepts of before and after lose their meaning. In this realm, space and time are not a fixed backdrop, they are dynamic, fluctuating entities. But what could this foam be made of? Leading candidates offer mind-bending answers. Loop quantum gravity proposes that space is not continuous, but woven from tiny, discrete loops, a fabric of interwoven threads of gravity itself. In this view, you cannot divide space infinitely. There is a smallest possible volume, a quantum of space. String theory, another contender, suggests the fundamental ingredients are not point particles, but vibrating strings, and the dimensions of space-time emerge from the way those strings vibrate and interact. In both pictures, the smooth cosmos we experience is an illusion, a calm average of unimaginably frenetic activity at the smallest scales. This is not just philosophical speculation, it is a hypothesis we can test. If space-time has a fundamental graininess, then it should leave a subtle fingerprint on everything that travels through it. Think of it like looking at a distant city through a window made of frosted glass. The fine details of the cityscape become blurred. Astronomers are applying this logic to the most energetic light in the universe, gamma-ray bursts. These colossal explosions emit photons of vastly different energies. If space-time is smooth, all those photons traveling billions of light-years should arrive at the same time. But if space-time is grainy, like running through sand, the higher energy photons might stumble ever so slightly more than the lower energy ones. Over cosmic distances, that stagger could become detectable, a blurring in the arrival times of the gamma-ray pulse. So far, the data from telescopes like the Fermi Gamma-Ray Space Telescope shows no such blurring, suggesting that if foam exists, its grains are even smaller than we've probed. Another ingenious approach uses not the vastness of space but the precision of time. If space-time is foamy, then the very flow of time itself should exhibit a subtle jitter, a fundamental uncertainty in measuring intervals. Scientists are testing this by comparing the world's most precise atomic clocks. These clocks, based on supercooled atoms or single ions, are so accurate they would not lose a second in billions of years. By comparing two such clocks or by watching a single clock over time, physicists look for tiny, random variations in the tick rate, a signature of time itself bubbling at the quantum scale. So far, the ticks remain perfectly steady, pushing the scale of any potential graininess even further down. These null results are not failures, they are the process of science closing in. Each experiment that finds no foam tells us the universe is smoother than we thought at that scale, narrowing the possible theories. The search continues with proposals to use pulsars as natural galactic clocks, or to look for interference patterns in massive particle detectors. We are probing the frontier where our classical concepts of space and time dissolve. The answer, when it comes, will not just tell us if reality is pixelated. It will reveal whether the universe is, at its heart, a continuous symphony or a cosmic mosaic, a discovery that would finally unite the worlds of the very large and the very small, and show us the true face of the stage upon which all cosmic drama unfolds. We have walked to the very edge of the map where the known world gives way to a wilderness of questions. 30 profound mysteries, from the ghostly pull of dark matter to the grainy fabric of space-time, are not failures of science. They are its beating heart. Each unanswered question is a frontier, a signpost pointing toward a deeper layer of reality we have only begun to glimpse. The universe is under no obligation to make sense to us, and it is in that beautiful, frustrating gap between what we know and what we wonder that all discovery lies. Not knowing is not an end, it is the very engine that drives us forward, that compels us to build bigger telescopes, dream bolder theories, and send silent probes into the dark. So the next time you look up at the night sky, do not just see the stars, see the questions, see the silent, waiting mysteries in the spaces between them. That curiosity is our greatest gift. Follow the journeys of the James Webb Space Telescope as it peers into the cosmic dawn. Listen for the news from gravitational wave observatories like LISA, which may hear the ripples from the universe's first second. The answers are out there, hidden in the data, waiting in the equations, sleeping in the light of distant stars. The story is not over. It is being written with every observation, every calculation, every wondering gaze upward. Which of these mysteries keeps you looking at the sky? Let us know in the comments below. And if you want to join us for more deep dives into the wonders of space and science, be sure to subscribe. The greatest discoveries always begin with a question.